Okay, so welcome to lesson 1. Today's topic, we'll be talking about number theories. So the first concept we're going to go over is divisibility rules for whole numbers. And when we say a number is divisible by another number, we mean that if the numbers are divided, the remainder will be 0. So for example, 6 divided by 2, that will give us 3 with the remainder 0. So 2 would be divisible by 6. So now the divisibility rules. So the divisibility rules we're going to go over today will go from 2 to 11. Some of you guys might have known some of these, but some of you might not know some other ones. So the first number actually that's not between 2 and 11, but we'll just say anyways, is that 0. So 0 is technically divisible by everything, as we like 0 divided by 6 will give you 0 with a remainder of 0. But also nothing is divisible by 0. So for example, 6 divided by 0, that would technically be not possible. And the next number we're going to go over, again, it's not from 2 to 11, but we'll just talk about it anyways, is 1. So, we can do, yeah. Everything is divisible by 1 because, well, everything over 1 is still that number with a remainder of 0. And the first actual divisibility rule we're going to go over is 2. So a number is divisible by 2 if the number is even, or we could do another check by seeing if the last digit is equal to 0, 2, 4, 6, or 8.
Zero, 2, 4, 6, and 8. And from now on, we will give examples for all the divisibility rules. So for example, for 2, a number that is divisible by 2 is 24, because the last digit of 4, it ends in a 4. Another example is 48, because it ends in an 8.
Yeah. And the next number we're going to go over will be the number 3. So this is a little more complicated. So to find if a number is divisible, what we first do is that we sum up all the digits of the number and then see if that sum is divisible by 3 itself. And another note is that this process is repeatable. So even if you summed up the digits and you feel like the number is still too big, you could sum up the digits to that new number and apply this rule over and over again until you find a number that's like small enough for you.
Example, we could do something like
69.
213. So how we would determine if this is divisible by 3 is by adding all of the digits together. So in this case, we have 2 plus 1 plus 3, which gives us 6. Since 6 is clearly divisible by 3, then we know that the 213 is also divisible by 3. David, do you want to give another example?
Sure, we could have the number 69. And when we add it up, we would find that 6 plus 9 is equal to 15, which is indeed divisible by 3. But we can demonstrate how it can be repeated by finding if 15 is divisible by 3. We could add 1 plus 5, which would give us 6. And here we know that, like the previous number, 6 is divisible by 3. So 69 is divisible by 3. So the next number is the number 4. So it's very similar to the rule of the number 2, but this time we check if the last 2 digits is divisible by 4. So we can move on to an example. We can use like an example number 2048. And we can see that the last 2 digits, 48, is indeed divisible by 4. So we know that the whole number is divisible by 4.
So now we're going to move to divisibility rules for 5. For 5, the number is divisible by 5 if the last digit is 0 or 5. As an example, we have 10. Since 10 ends in a 0, it satisfies the divisibility rule for 5. Another example would be 25. Since the last digit is a 5, it is also divisible by 5.
So for the number 6, it's a divisibility rule is actually combined from 2 other divisibility rules. So as long as the number is divisible by 2 and 3, then that number is divisible by 6. Kevin, do you want to give an example?
Sure. So as an example, we have 24. We first check if it's divisible by 2. It is divisible by 2 because the last digit is a 4, so it satisfies divisibility by 2. Next, we check if it's divisible by 3. So we will add the digits together to see that we get 6. Since 6 is divisible by 3, 24 is also divisible by 3. Thus, since 24 is divisible by 2 and 3, 24 is also divisible by 6. Another example would be 96. So we first check if it's divisible by 2. It is because the last digit is a 6. Now we check if it's divisible by 3, and it also is because 9 plus 6 equals 15, and then 1 plus 5 equals 6, which is divisible by 3. Thus, when both of these conditions are satisfied, we have 96 is divisible by 6.
So our next rule is for the number 7. So this one's a little more complicated, so we would give a little more examples for this. So the rule states that if the absolute value of the difference between the last digit doubled and the rest of the digits as a single number is divisible by 7. So we could have an example like the number 63. So we take the last digit, which is the number 3, and then we double it, which would give us 6. And then we take the rest of the digits, which in this case is only 6, and subtract the 3 doubled from it, which would give us 0. And we could also just absolute value that if it's negative. And we know that 0 is divisible by 7. So that means that the 63 is divisible by 7.
Right. Another example that we could do is 77. So when we take the last digit and double it, we get 14. When we move this 7 over, we get 7 minus 14, which is negative 7. When we take the absolute value of it, we get 7. Thus, it's also divisible by 7. Now, another number we could do is 147. In this case, we have 7 multiplied by 2, which is 14, and we move the rest of the digits over. So it's 14 minus 14, which is 0, which is also divisible by 7.
Now the next number we're going to go over is the number 8. So this one's very similar to 2 and 4, but it states that the last 3 digits is divisible by 8. So we can have an example with like the number 560, which we would see that 560 is the last 3 digits, 560, is indeed divisible by 8. Another way we could check this is that we could start working up from 2. So we could check if it's divisible by 2, and then check if it's divisible by 4, and then at last check if it's divisible by 8. So we don't have to like straight up just use 8. We could use like the smaller ones first.
Yeah. That's right. And for this example, 560, since 560 is divisible by 8, we can also have 1,560 also divisible by 8. We can have 2,560. We can have 3,560. We can have 48,560. As long as the last three numbers are divisible by 8, the entire number is also divisible by 8.
So the next number we're going to go over is the number 9. So this one is very similar to the number 3. What we do is that we sum up all the digits in the number again and check if that new number is divisible by 9. So we could have like a simple example with the number 45. We could see that if we add the digits 4 plus 5, it gives us 9, which is divisible by 9. So we know that 45 is divisible by 9.
Another example would be 1,233. When we add up all the digits, we have 1 plus 2 plus 3 plus 3, which also equals to 9. Thus, it's also divisible by 9.
So the next number is a number 10. So in this case, if we want to know if it's a number divisible by 10, we would just see if the last digit is 0. So as long as the last digit is 0, it's divisible by 10. Kevin, do you want to do an example?
Sure. We can use our example 1,560. Since the last digit is at 0, then this number is divisible by 10. We can also have 2,570. And since the last digit is at 0, it's also divisible by 10.
Now our final number to check is the number 11. So what we do is that we grab the difference of the sums of the alternating digits and check if that new number is divisible by 11.
This one is a little more complicated, so we're going to give more examples.
Let's have a big number example, like 77,616. So what we do is that we could first mark out the alternating digits. So we could see that we could group the numbers together like 7, 6, and 6. So those will be one group. We add all those up. And then we add up the other group, which is 7 and 1.
We have 7 plus 6 plus 6.
And then we subtract that from the other group.
7 plus 1. And we get 19 minus 8.
That gives us 11, which is divisible by 11. So we know that this big number is divisible by 11. Should we do another example?
Yes, we should.
So we can have the number 869. And we can group up the alternating digits. 8 and 9 go together. And 6 is by itself. And then we can add up 8 and 9 and subtract 6 from it. And we can see that the new number is 11, and that's divisible. So 869 is divisible by 11.
Yeah. And another notice is that if the number is -11 or -22 or -33 and so on, it's also divisible by 11. We can have any number that is, okay, the absolute value of number is divisible by 11, then the entire number is also divisible by 11.
So for example, we have the number 28 to test the rules on. So we could go through each rule. We see that obviously it's divisible by 1. And We could also use our rule of the 2. We see that the last digit 8 is divisible by 2, so we know that the whole number is divisible by 2. And then we also know that it's divisible by 4. It doesn't end in 0 or 5, so it's not divisible by 5. And the same goes for 6 because we don't have the number 3. But we can see that when we apply the divisibility rule for 7, it is indeed divisible. And since factors always come in pairs, we could kind of fill out the rest. We know that 28 divided by 2 gives us 14, so that's another factor. And divided by 1, that gives us 28, so that's another factor. We can move on to our next concept. Do you want to do that?
Sure. So
Okay.
now that concludes the factoring unit. Next up, we're going to look at the fundamental theorem of arithmetic.
So this fundamental theorem states that every whole number is either a prime number or can be represented by a unique product of prime numbers. So we can go through a little bit of a definition again. So prime numbers are numbers which have two distinct factors, which is 1 and itself. And then we also have composite numbers, which are formed by multiplying two other numbers. So an example of this would be like the number 6. It can be multiplied by 1 times 6 or 2 times 3. And do note that 0 is not a prime because 0 is divisible by everything. So it's more than two distinct factors. And 1 is not a prime because it does not have two distinct factors. It only has one.
So we're going to learn what a whole number means in our next unit, but just as a brief overview, a whole number is 0, 1, 2, 3, and so on. They start from 0 and they don't have a decimal component to it.
And now the question is, how do we find these prime numbers? We could use the concept of prime factorization. So prime factorization is a process of finding which prime numbers multiply to the original number. So there are two main ways that we're going to learn about. The first method is the factor tree method, and the second method is a division method. So the first method we're going to learn about is a factor tree method. So what we're going to do is that we're going to build a tree of all the factors that make up a number. So for example, we can have the number 48. And then we could find two of its random factors. Doesn't have to be a specific one, like 8 or 6. And then we could go off one of the branches, like the number 6, and we could find the factors of 6, which we find are 2 and 3. And we know those are prime numbers, so we can't break those down any further. So we just move on to the next branch, which is the number 8, which we can split into the numbers 4 and 2. And then we could break down the number 4 into 2 and 2. And we notice that the numbers at the bottom of every branch is a prime numbers. And once every branch has a prime number at the end, that means our factoring is done. So those numbers at the bottom are the prime factors of 48. And that would be how we represent a prime factor.
However, if we want to condense it, we can write this in a power notation. So 2 to the power of 4 times 3. That's how you would simplify it.
And the next method we're going to go over is the division method. So this one works in the same concept as a factor tree, except we do division, as the name implies. So we could try a bigger number this time, like the number 960. So we could start from the smallest prime numbers that we know. So we could divide 960 by 2 is divisible. And we can see that it is. And it gives us 480. And then we can see that this number is also divisible by 2. It gives us 240. And then we could do this process over and over again. 120. And then we can do it again. And it gives us 60. And again. And it gives us 30. And again, and it gives us 15. And now we see that we can't divide by 2, but we can move on to the next prime number, which is number 3, and it is divisible. And it gives us 5 at the very end. And we know that 5 is a prime number, so the entire thing stops here. And those numbers on the side and the very last number is a prime factorization of 960.
So it is these numbers that are the prime factors. Now, use this method if you have a very long piece of paper, because it's going to be very, very long. Use the previous tree method if you have a wide piece of paper, because it's going to go very wide.
Yes, there's not really a method, like a difference between the method, except for like organization, which is kind of important.
Yeah.
And so the next topic will be greatest common factors. So the definition of a greatest common factor is essentially the greatest factor that is common to all the numbers, which you, well, to both numbers. We could use an example of this.
You can have multiple numbers.
Yeah. An example of a greatest common factor would be like the greatest common factor of 10 and 15 would be 5. And that is a notation you will use to represent the greatest common factor. Kevin wrote GCD, which stands for greatest common divisor, which is basically a synonym of greatest common factor. Your teacher might also refer to it like that.
Yeah.
And we could do another example of this. So we can say that the greatest common factor of 6 and 12 is 6. So another concept we're going to go over right now is that if two numbers only have a greatest common factor of 1, then we call those two numbers being relatively prime. So they might not be prime numbers, but when we find the greatest common factor, it's always 1.
They're called relative primes, but they're also called coprimes. So
Yes.
relatively prime or coprimes. Another example is 2 and 13. They only have a greatest common divisor of 1. So they're also coprimes. Now, the definition of a coprime is very important in fractions, because in a fraction, you want to reduce it to the lowest common factor. So for example, we have 8 over 4 is equal to 2 over 1. Now, basically, when we reduce a fraction, we mean we extract out the common divisors until it becomes a coprime. So we divide by 2 to get 4 over 2, then we divide by 2 again to get 2 over 1, and we do this until they both become coprimes.
So we can actually use a previous method we talked about, prime factorization, to find the greatest common factor of some set of numbers. So we can do this with an example. So we can try to find the GCF of 20 and 30. We can use the example of 20 and 30. So the first step to this method is obviously to prime factor the numbers. So we could prime factor 20, which would give us 2 times 2 times 5, or 2 squared times 5, and then we could prime factor 30, which gives us 2 times 3 times 5. And then what we do is that we spot common factors. So in this case, 2 is common to both sets, and 5 is common to both of the numbers. And in this case, we always take the lowest exponent. So we don't take out 2 squared, but we take out 2. Oh, and Kevin's doing the aligning method that he always uses.
So just so it's easier, before we go on to David's step, we want to align these numbers so they have the same base, right? Then, as David said, we take the lowest exponent of D2. So all the numbers by themselves are just to the power of 1. So let's look at the base of 2. We take the lowest exponent, which is 1. Then we take 3 to the power of 0. Then we take 5 to the power of 1, which gives us 10.
Which would be the greatest common factor. So we can do another example with the numbers 24 and 64. And we could prime factor both of these out. 24 gives us 2 cubed times 3, and 64 gives us 2 to the power 6.
Oh, whoops. 6.
And we can do the aligning method. And then we could take down the lowest exponent, which would be 3. So 2 to the 3. And then it's 3 to the 0. And that would be your greatest common factor, which would be 8. And we could do another example, but this time with 3 numbers. And it still works the same way. So we can have the numbers 18, 24, 18, 24, and 42. And we could prime factor all of them out. And the prime factorization of 18, the screen freeze? Oh, no, okay. 18 would give us 2 times 3 squared. 24 would give us 2 cubed times 3. And 42 would give us 2 times 3 times 7. We could do the aligning method. And we could bring down the lowest exponent, which would be 2 to the 1, times 3 to the 1, times 7 to the 0. And the GCF will be 6. So we can do another example to show a relatively prime. So we could try to find the GCF of 9 and 14. And we could prime factorize them. And then 9 would give us 3 squared. And 14 would give us 2 times 7. And when we do the aligning method, we can see that nothing matches up, which would mean that all of them will be to the power 0, which would give us 1. So we could say that these two numbers are co-prime or relatively prime.
Next up, now that we know what the greatest common factor is, we're going to move on to the least common multiple. And in some ways, these are both related to factors. The definition of a least common multiple is the least number, the smallest number, that is a multiple of both numbers. It can't be 0.
So we can do an example of this. So we could say that the least common multiple of 10 and 3 is 30. And that would be the notation LCM. So We could do another example. We could say that the least common multiple between 3 and 6 is 6. And do note that for the first example we gave, we could have multiplied the numbers together and it would have gave us the LCM, but that will not always be the case. When we multiply the numbers together, it will give us a multiple, but it's not always the least common multiple.
Yeah, and the only case where when you can multiply the numbers and get the least common multiple is only if they are co-primes. So if the two numbers are co-primes, like 10 and 3, then you can multiply that to get the LCM.
So like GCF, we can use prime factorization to determine the LCM. So we can do an example of this. We have to try to find the LCM of 8 and 20. We can prime factorize them both out, and we see that 8 is equal to 2 cubed, and 20 is equal to 2 squared times 5. And in this case, we can also do the aligning method, but it's already lined up. And in this case, we actually take the highest exponent. So we actually take down the 2 cubed instead of the 2 squared, and we actually just take down the 5 because that has the highest exponent. And that will be our LCM. We could do another example with the numbers 8 and 42. So we could prime factorize both of them. 2 cubed and 42 is equal to 2 times 3 times 7. And we can do it the aligning method, or it's already lined up. And we take down the highest exponent, which is 2 cubed, and then the 3. And then we can take down the 7. And our new LCM will be 168. So we could do another example with 3 numbers. So we could have the LCM of 3, 6, and 14. And we could prime factorize all of them. 3 is already a prime, so we just carry it over. And then 6 is 2 times 3. And then 14 is 2 times 7. And we take down the highest exponent, so we take down the 2, the 3, and the 7. And that'll give us 42 as the LCM. And I believe that's the entire class of number theory.
Yeah. So now that we finished the number theory lesson, we have put up some worksheets and some quizzes onto the public Google Drive. They both have answers attached to them, so you can do them on your own time and just try some of the questions out. But yeah, have fun.